In this section, we'll talk about the line integrals. So line integrals arise from integrating a function along a curve C in the plane or in space. For a two-dimensional line integral, suppose that we have a smooth curve C, where a smooth curve means a curve that has a tangent vector that is continuous and non-zero. And that curve is given by the parametric equations x equals to x of t and y equals to y of t, where a is less or equal to t less or equal to b, or equivalently, the curve is given by the vector equation vector r of t that is equal to x of t times the vector I plus y of t times the vector j. Then if we have a two-variable function f of x comma y that is defined on the curve C, the line integral along the curve C of the two-variable function f of x comma y times ds will be equal to the limit as n approaches infinity of the sum from I equals to 1 up to n, where n is the number of sub-arcs we divide the curve C in, of the function f of xi star yi star times delta si. And essentially what we do here is we divide the curve C into n sub-arcs, where each sub-arc has a sublength delta S1, delta S2, up to delta Sn, and we choose any point pi star with coordinates xi star, yi star in the ith subarc. Now, if we denote as s of t the length of the curve C between two position vectors Ra and Rt, the derivative of the length of the curve with respect to t will be equal to the square root of dx over dt to the square plus dy over dt to the square, and therefore the line integral along the curve C of f of x comma y times ds will be equal, and now we convert everything with respect to t. So it will be equal to the integral from a up to b of the function f, where x is expressed as a function of t and y is expressed as a function of t, times the square root of dx over dt to the square plus dy over dt to the square times dt. Or in short, the line integral along the curve C of f of x comma y times ds is equal to the integral from a up to b of the function f evaluated at the vector equation times the magnitude of the tangent vector times dt. Now, how can we interpret the line integral? So just as for an ordinary single integral, we can interpret the line integral of a positive function as an area. So if we have a function f of x comma y that is greater or equal to 0, then the line integral along the curve C of f of x comma y times ds represents the area of one side of the curtain. So this is the curtain that we have. So this represents the area of one side of the curtain whose base is the curve C. So this is the curve C, and whose height above the point xy is equal to f of x comma y. Let us see an example. We're asked to evaluate the line integral along the curve C of x times y to the fourth times ds, where the curve C is the right half of the circle x squared plus y squared equals to 16, oriented counterclockwise. So let's first of all sketch the curve C. So it's only the right half of the circle, and the circle is oriented counterclockwise. And therefore, the equation of the circle, x squared plus y squared equals to 16, can be parameterized by the equations x equals to 4 cosine t and y equals to 4 sine t. And in order to get only the right half of the circle, we see that t will take values between negative pi over 2 up to pi over 2. So t will be in the interval from negative pi over 2 up to pi over 2. So the two equations for x and y with respect to t, with the interval for t, describe only the right part of the circle. And therefore, the line integral along the curve C of x times y to the fourth ds will be equal to the line integral along the curve C of x times y to the fourth times ds is equal to the square root of dx over dt to the square plus dy over dt to the square times dt. And we can evaluate the dx over dt from the fact that x is equal to 4 cosine t. So dx over dt will be equal to negative 4 sine t. And also we have that dy over dt is equal to 4 cosine t. And we can now express everything with respect to t. So we'll have the integral from negative pi over 2 to pi over 2 for t. X is equal to 4 cosine t. So we have 4 cosine t times y to the fourth, which is equal to 4 sine t to the fourth, times the square root of dx over dt to the square, which is equal to negative 4 sine t to the square, plus dy over dt to the square, which is equal to 4 cosine t to the square, times dt. And all the square root here is equal to the square root of 16, which is a common factor from the two terms that we have, times the sine squared of t plus cosine squared of t from the two terms. This is equal to the square root of 16, which is equal to 4. And therefore we have a 4 from here with a 4, and a 4 to the fourth will give us a 4 to the sixth, which we can pull out. So we have a 4 to the sixth integral from negative pi over 2 up to pi over 2. And what remains is the cosine of t times sine to the fourth t dt. And here we can do a u substitution. So substituting u with sine t, we have that du is equal to cosine t dt. So therefore, the integral of cosine t times sine to the fourth t dt will give us the integral of u to the fourth du, which is equal to 1/5 u to the fifth plus a constant c, if we had an indefinite integral, and this is equal to 1/5 sine to the fifth t plus c. And substituting all that, we have a 4 to the sixth, which we had from before, and then we have 1/5 sine to the fifth t, and we now put the normal bound, so we have t from negative pi over 2 up to pi over 2. So that is equal to 4 to the sixth divided by 5. And then for t equals to pi over 2, we have sine to the fifth of pi over 2 minus sine to the fifth of negative pi over 2. So that is equal to 4 to the sixth divided by 5. And then sine to the fifth pi over 2 will give us a 1 minus sine to the fifth of negative pi over 2 will give us a negative 1. So that in total is equal to 2 times 4 to the sixth divided by 5. And if we compute that with a calculator, this is equal to 1638.4.